Yeah, hi. Good evening, everyone. So today is week 4 live coding session, basically problem solving session we have, and I hope you have done this week 4 content till now. So in week 4 we are learning this graph algorithm, and these are basic graph algorithms. And so today we will discuss three programming problems, and these problems are basically based on that graph algorithms which you have already learned. So let me first thing, please join this Replit team, okay? And we will use this Replit team, and the Replit team link. If you have not joined yet, the invitation link is already given in the calendar event, okay? Otherwise, you have already joined in the previous session, so you can directly open, and then we will start. Okay. Before starting, if anyone have any query, any question, you can ask. Okay. I'm sharing my screen. I hope I'm audible. Can anyone confirm? Okay, Sahil.
Yes, sir. You're audible.
Okay, okay, fine. Yeah, so I'm releasing the problems of week 4, and these problems already released on the portal also. Okay, so you can also see the problem on portal. But during the live session, we will use this uh, Replit team. Yeah. Now all problems are released, and you can just refresh your page. So if you are not able to see the problem, just refresh the page, and then you can see the week 4 problems. Okay, so three problems are there. So let's move start with problem number 1. So we will discuss during solving these problems. We will discuss about that what are the basic area where these algorithms actually used. It may be used. So in if you can try on the that competitive platform also, so they ask at the time of designing the problem, they also actually use the algorithms, and they just create some scenario based on that, based on the algorithms, and they just add some story and some scenario, real life scenario, and after that they ask the questions. Okay, so same things. Today we have some problems which are related to this competitive type of real life scenario. So let me open the first problem statement. Okay. So this is the problem statement. You can see on the screen. And then we so just you can also read the problem statement and try to understand the problem statement first, and then figure out which of the algorithm is most suitable for this and how you can approach this question. Okay. So I am reading the problem statement. So the problem statement for first problem is the express train routes are provided in the adjacency list. Name of the adjacency list is A list. Here you have to find the route from start to end. Okay, with minimum number of hopes possible. Okay, so that means you need to find out the route from start, some start vertex or that start node to end node with minimum number of hopes in between. Okay, so including this start or end, minimum number of hopes should be come in between in the path. Write a function minimum hopes, and that function takes these arguments, that A list, this is adjacency list for root, and start vertex and end vertex, to return the cities to be visited starting from start to end. Return a list with only start if the end is not reachable. Okay, so this is also a one constraint which is given in the problem statement. If you are not reachable to the end from start, okay, if there is no path is available, then just return a list with only start vertex. Okay, so this is problem statement. You can see what is the structure of a list. This is a adjacency list You can see this in the sample input, and this is created in the dictionary form. So if you know that we are using this adjacency list in the form of dictionary in Python, where we can directly access the key. So this key is representing the source, and these value inside the list corresponding to this key is representing the nodes that are directly reachable from this key node. Okay, so that means we have some edge directly from 1 to 3, 1 to 5, 1 to 8. So we can figure out that if we want to check what are the direct neighbors, or we can say that neighbors of the three that vertex 3, which are directly connected to 3. So we can directly check the list, and we can figure out these are the vertex which are directly connected to 3. So this is the use and of the adjacency list, and we have this another variable start and end, and you need to return the output in this manner. So that means start vertex is 8, and this is end vertex. So what is the path from 8 to 7? Okay, so you need to figure out this path, and this path should be shortest in the terms of minimum number of hop in between the path. Okay, so 8, that path means 8 to 9 you have to move, then 9 to 1, 1 to 3, then you can move to 7. So this is the shortest path, okay, from 8 to 7. So that this is the list, but in output we are only checking that how many actually hopes are there in the path. So this is the sample output for this problem. Okay, so that means your code will return this, but suffix code will check the length of this list, and that it will be print 5. So that means in path 5 vertex are coming. This is one graph, so like 8 to 7. So what are the shortest path possible from 8 to 7? You can just figure out that. So 8 to 9 you can go. So 8 to 9, then 9 to 1, and 9 to 1, and then 1 to 3. So 1 to 3, and 3 to 7. So this is actually a shortest path in the terms of new number of node in between. Okay, so this is the problem. I hope the problem is clear. If anyone have any doubt in to understand the problem, basically, so first thing, when you are solving the problems, so this is the first step. The problem statement or problem should be clear. Or step, okay.
Sir, so
Yes,
it is deciding the shortest path based on the least number of node it has to travel, it has to visit.
yes,
Vertex, yeah.
yeah, vertex. So in path, actually, the vertex should be minimum in all possible path. Okay, so
Mm.
there are multiple possibility that you have multiple path from any source vertex to that destination vertex. But you need to choose the path which is actually shortest. Shortest means shortest in the terms of minimum number of edge in between, or minimum number of hopes node in between. Okay, not we are not using any distance on the edge. This is simple unweighted graph. Okay, you can see there is no weight, but this is a directed graph.
So basically, we store the number of vertex we need to visit that in a separate list, and whichever list will have the minimum number of element, that is the selection.
So that how you can figure out the route first. First thing is you need to figure out the shortest path. What is the approach? What should be the approach for this?
We need to start from the starting node and then do a breadth-first search.
Breadth first search. Okay. So
Yes.
why you are selecting this breadth first search? Why not
Be-
DFS?
because DFS doesn't necessarily finds the shortest path.
Okay. And how this BFS is actually found this shortest path?
Because from starting point, it will view all the nodes. We like stored the nodes in the queue, and then like by layer, it will view the nodes. And then in the first place, in the first layer, that is the our ending point is coming. We will see that.
Okay. So according to the approach of BFS, so both are actually traversing algorithm, BFS and DFS. But BFS actually traverse the nodes in that adjacent node wise. Okay, so it layer wise like this. Okay, so if we are, suppose we are starting from 0. Okay, we are starting from 0. So that means this BFS algorithm will traverse all the nodes which are directly connected to this 0. Okay, so that means 0 to 8, only 8, one vertex is there, so it will traverse this node first. After that it will check, so there is no other possible path direct connection from 0. Okay, so after that we will check from 8. So what are the neighbors which are directly connected to this 8? Okay, so just check the outgoing edge from 8. So what are the possible neighbors for this? So only we have 1. Okay, so 8 to 9, you can see there is one outgoing edge from 8. Okay, so this is 8 to 9. So this is the traversing. So this is the next level. We can see that BFS is traverse the node neighbors wise. So all that it will traverse all neighbors first, then it will move to the next neighbor level. So here from 9 again.
Sir,
Yes.
does it 7 is also a neighbor of 8?
No. So here actually this is a directed graph. So
Okay.
direction is representing the movement also. So if 8 to 7 you cannot move because the direction is just
Yes.
opposite.
Got it.
Okay, so 7 is not will be considered as a neighbor. Okay, so we will check the direction here. If direction is not given, then we will simply consider as a neighbor. So now 8 to 9 is possible, only one neighbor. So this is the only possibility. After that, from 9, you can see there is only again one outgoing edge. So it will traverse 1. And then from 1, again one outgoing edge. So yeah, no, okay, but we have already traversed 8. So we will not traverse again. So from 1, you can see only one outgoing edge is there. No, 1 is also, this is also there. Okay, so 3 is also there. To here direction is giving both side. Okay, and 5. So here this is the way to traverse. So that means after 1 we will traverse both neighbors of the 1. So that is 3 and 5. Okay, any other neighbor is there? No. Okay, so now this is the next traversing. So we will traverse both neighbors first, 3 and 5. And from 3, so we will check what are the possible neighbors which are not visited. So 3 to 7 and 3 to 2. Again, two neighbors are there. So 3 to 7 and 3 to 2. So both are now traversed. And from 5, so you can see 5. So where is 5? This one. Okay, so 5 to 4 we can only traverse. So this is the next traversing. So 4. Okay, so this is we are just directing. We are using the BFS way to traverse. Okay, now from 7 to 8 we can traverse, but 8 is already traversed, so we will not traverse again. Now from 2 you can see we can traverse 9. 9 is already traversed. Okay, and you can also traverse 8, but it is again already traversed, and there's no another node. Now from 4 to 6 you can traverse. Okay, so 4 to 6. This is the next. And 6, now there is no node remaining. So this is the 0, and then 8, 0, 1, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 vertex we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So all nodes are now traversed, and this is the tree we are getting, and in that when we're traversing using the BFS algorithm. Okay, so traversing this traversal is actually generate traversal tree, and in traversal tree you have some path from each node. Okay, each node to another node. Okay, so you can travel, and this is the only one possible path in this tree. So 0 to 7 you can see only you have this on this path. Okay, so this one. Okay, and 0 to 6, suppose you want to go, this is the only one path, and this path is actually a shortest path in the terms of minimum number of edges in between. Okay, so if you count the edge, or if you count the number of nodes in between, or okay, including the source and destination, so this path is actually shortest path. But if we suppose if we apply DFS, so DFS there is no restriction to traverse neighbors wise, DFS follow the approach to traverse depth wise. So from zero, only one node is there, so it is fine. So if there is one possibility, then it will move the same into the same way, then 9, then 1. Okay. After 1, if suppose DFS is traversing 3 first, okay, 3. Then after 3, it will traverse only any one depth. Okay, so again it will traverse like this. Suppose 2, it is traversing 2, and from 2 it will check the remaining vertex. Okay, so like 2 both are now visited, so that is fine. If there is no possibility, then it will come back to the previous node and will check the remaining node. So suppose if from 2 only there's 2 possibility, 8 and 9, so both are visited. Now it will come back to previous node 3, and from 3 it will check again. So what are the another possibility from here? So from 3 it will traverse the next node 7. Okay, and from 7 same, it will traverse 8. 8 is already traversed. Now there's no possibility, then it will move back and move back to 1, and from 1 it will check the another path. So this is like this. So we are getting, for this example, we are getting, I think, same tree like as a BFS, because here there is no other way to join. Okay, but what happens, suppose if any node is connected to the another node, so you will get the different path. Okay, so but here we are getting only one possible, so this 4 and 6 both same tree. But DFS approach is basically to enter into the direction, the depth first. Suppose if you have like this, so this is suppose A, and this is B, this is C, like this. Okay, okay, we are traversing from, suppose this we are traversing this vertex, this graph from A. Okay, so from B, if we suppose use BFS, so we will get like traversing like this. So then B and then C both adjacent. Okay, so from B we will traverse D first, then from C we will traverse E and F. So this we will get from the BFS. But if we apply DFS, then we will get A, then after A, then we will traverse B. Okay, so we will not move to C, we will complete the depth of this first path. Okay, then we will traverse D. Okay, and from D we will move to this E, like this. Okay, so then F, then there is no possible path from F. Okay, now we will come back to A, and again we will traverse C. So this is the way to traverse of the DFS. So here you can see we are getting different tree. So but this BFS actually ensure that we will get the shortest path in the terms of number of hopes. So here you can use the BFS algorithms, but yeah, so some code is already given in the code, that code part, that main.c. So you can see this prefix code is already given. You can use this code and you can figure out the path. Okay, so if you have already done this code, this is the code which is already discussed in the course content lecture. Okay, and this code is basically traversing the that graph, and it is also maintaining the label number, which label actually we are visiting for each node, and it is also maintaining the parent information for each node. Okay, so that means finally this code will return the label for each node, which label actually we have for each node, and it will also return the parent information. So that means what are the parent for each node, where from we are coming on that node. So that information this code is actually returning. So this is BFS list path label. Okay, so this is discussed in the lecture, and now this is the return things, return label and return parent. This two dictionary, basically this code is returning to the by the function, and this parent is here actually useful because you need to figure out the path from source to destination. So how you can figure out the path if you have this parent information for each node? So here your task is not too big, just use this function and just find out the path. Okay, so write the main function here. That function is actually require this minimum hopes, and this inside this function, call this function bfs list label. This function will return a that label and parent information. After getting this parent information, use this parent information. I think label information is not required, so use this parent information and return the list of that path vertex. Okay, so I am just telling you the approach how you can solve this. So you are getting a dictionary of the parent. Suppose you have the vertex like this. So for the previous example, for the same graph. Okay, so here actually we are getting this bfs will perform on this, and this bfs actually will return. Uh, so by this process, bfs will return the information, the parent of each node. Okay, so here you can see 0, and we have applied the algorithms, that bfs algorithms, on 8 vertex. Okay, so that 8 is the source actually. So this 0 will not come here, 0 will come like here. Okay, yeah, because we are starting this 8. Okay, so now in the dictionary, what parent actually will return. So this parent dictionary will come look like this. uh, Inside the dictionary, what are the parent of 8? Okay, so 8 is the source vertex, so parent will remain -1 for this. Okay, so you can see the implementation in the code bfs. Initially we are assigning this parent of I equal to -1. Okay, so that means if we are not getting any parent for I vertex, so that means it will remain -1. So source doesn't have any parent, so it will remain -1. After that, you can see on 9 where from we are coming. So what is the parent of 9? So 9 parent is 8, 1 parent is 9. Okay, what is the parent of 3? That is 1. And what is the parent of 7? This is 3. And what is the parent of 2? This is 3. And okay, what is the parent of 5? 1. Parent of 4? 5. And parent of 6? 4. Okay, so this dictionary will be returned by the function which is already given in the code, and you can use the backward approach that from this. So what is the destination is given in the problem statement. Okay, so for this input, so 8 is the source and destination is the 7. Okay, so this value is given in the input, so this is the destination 7. So you can just traverse reverse. Okay, so from 7, just check what is the parent of 7. Okay, you have this all this information in this parent dictionary. So check in the dictionary what is the parent of 7. So parent of 7 is 3. Okay, and repeat this process continuously until you are not reaching at the start word source vertex. Okay, so just repeat this process again and again. Okay, so now parent of 7 is 3. Okay, you can see here. Now check what is the parent, because 3 is not source node. Then again repeat the process. So what is the parent of 3? The parent of 3 is, you can see here. Okay, so 1. So you will get 1. Now still 1 is not equal to that source vertex. So again check what is the parent of 1. So parent of 1 is 5. Okay, so 5 from here, and again 5 is not source. Then what is the parent of 5? So parent of 5, sorry, one parent is 5. Okay, 5 mistakenly calculated, so 1 is not mentioned. Okay, one second, why I missed 1. So 1 is also there, so that one parent is 9. Sorry. So parent of 1 is actually 9. Okay, yeah, and what is the parent of 9 is 8. Okay, so you need to traverse, you have to start from the end vertex and just check the parent dictionary and find out the parent for each node and repeat this process. And when you are reaching at this 8, just stop. Okay, so you will get this list. So say this 8 9 1 3 7, you can return this list into the output, and that code will check the length of this. And after that okay, one second, let's start this part. Okay, and what if suppose if you're getting the -1 distance for end vertex? Okay, so just return the list like 8 only start vertex. So this is another constraint we have. Okay, so this is the problem you need to solve. Now I have explained the logic completely. Just try to solve this. Any doubt in this? Anyone have any doubt in the first problem logic? So these are some area. So like BFS, suppose what are the possible problems for the BFS algorithm? Is basically first is find out the shortest path. Okay, and shortest path not based on the distance. It is based on the number of edge or number of vertex in the path. So the problems may be created based on this scenario. And another is finding out the component, connected component. So that is also one application. So you can use that uh, connected component. That problems can also be created based on that. So you can figure out this. And another is like traversing base, you are reachable or not. That node is reachable from that, like this.
Excuse me, sir.
Yes, Taran.
Sir, I solved today PPA one, and I'm getting 4 out of 5. So means answer correct. So one is not correct. Everything else is correct. Can you just look at the code? Not this one, but PPA one.
PPA one for Week-4.
Yeah. It is upon. It is that component wise we have to do. We have to count the number of components. So I'm getting 4 answers correct, but one is not getting correct. So is it
Private
because
test,
of
yes.
complexity?
No, no, no. We are not checking any complexity for this.
Yeah.
So it is not given. Na? So we are not asking any complexity in the problem statement, you can see. So, but here maybe just read the each line of the problem statement. Like for a complete connected graph, there is only one connected component. Here the function should return 1. So like just read, follow all the constraint of the problem statement. Maybe you are missing some corner case.
Okay, sir.
Okay, so just figure out that what are the possible input according to the problem statement, and just try to write your logic accordingly. So you can take like this. Suppose if only one component is there, then your code is working fine. Multiple component are there, then what is your output? And also follow this for the below graph. This is the example, but this is one given things is there. And in the graph there is only one connected component, hence the output should, yeah, okay, this is also example. So maybe your code is missing some corner case. So just take each type of example for your graph and just test your code. Okay, anyone have done this code? That's problem number 1.
So,
Yes.
in this question number 1, we have to calculate V for passing the parameter to the bait cursor, right?
No, what you are calculating? Sorry.
Means we have to. They have given bait cursors BFS, and we have to pass the parameter to BFS, right?
So one second. So here actually this list is given a list. Okay, so this is the actually you need to write this function. Okay,
Yes, yes,
min hooks,
minimum
and
value.
here you need to pass this a list start end. You can also change the name in your function, but this these are the value which is passed in the function. Okay, this a list means this is a dictionary that represent the adjacency list for graph, and this is only a start vertex and this is a end vertex. But in your function you can change the name accordingly, what type of name you want to take. Okay, and in use only these all data which you are getting in the input. Okay, so some of them you have already done submitted code, like Sahil have done, Deepam, TK, Prince. Okay, so any one of you want to explain if you have done? So this actually path finding problem is also very important for the week 5 also. Okay, so in week 5 we will learn the shortest path algorithms. Okay, so where the distance will be given as a weight, but how you can figure out the path, find out the path. Okay, not the path distance only. So what will be the path actually? So this reverse backward things you should know. Okay, that will be useful for next week also. So how you can write code for this?
Sir,
Yes, Dave.
sir, do we have a deadline for this live coding? Like, should we have to submit today?
So you should submit today because this is the idea for this live coding problems. Because we want that you need to complete all these problems within 2 or 3 hours. For
Like,
practice,
we have
basically.
till 12.
No, we have not set any deadline. Okay, you can do tomorrow also, and on the portal the deadline is set to September. Okay, so you can do at any time, but we are just requesting to you just try to complete as soon as possible in 2 or 3 hours.
Yeah, okay, sir.
Okay, because sometimes if you leave the problems for the late, you will do later, but most of the time you will not solve after that. Okay, so you will get any another work, then you will not doing. So just try to complete all the problems in the session itself. Okay, so anyone have done? If you want to explain your code,
Yes,
Tarang, you have done. Okay, okay, nice. So in your code. Okay, and you can expect one problem definitely from week 4 and week 5. That means graph problem in the OPP exam. So just practice on that. Tarang, what is your ID?
so mine is 23F20046661.
4661. Let me check. This one. Okay. Okay. So this part is already given and you have written this part. Okay. So what you did, you okay, can you explain? Yeah.
Yeah, so first I took level and so I first of all I gave the BFS path level the starting index and got the level and parent dictionary from there, and then my target is the end vertex, and for the counter I took a variable I and a list which starts with the ending vertex, and
Okay.
then and then while parent of v means while the value while we don't get to the source, I append I and I append the parent of v to the list, and then I change the value of v to the parent of v.
Okay, so while parent v does not equal to -1, I plus equal to, so this I by you're calculating.
Sir, just for the means,
Okay,
I
okay,
think it is
count.
not, yeah,
It
for
is
the
not
complete,
required.
it is not required. First, because I thought that we have to send the number of input. Then I saw that we have to put a list.
Okay, okay, okay. So you are getting the list in reverse order, like from end to that source, correct?
Yes, just
Uh-huh.
the sir, the algorithm you explained the same thing.
Okay, okay. So yeah, that is fine. But this is not fulfilling one constraint. But yeah, your code will pass actually the test case,
Sir,
because
no,
according to, yeah, according to the
private.
process statement, it is given that if suppose if there is no path, then list should contain only source vertex. But
So
in
sir,
your
we can
case,
check at the end if L is not equal to length,
ha.
length of L is not equal to 2. We'll put
You
start.
can check. So after performing this operations, you can take empty list and you can perform this appending things. And in later you can check if your list is empty, then append only the source and
Yes, sir.
then return. So that you can
The
do. Yeah.
level to check also, right?
Sorry.
You can use the level to check also, right? Level of ent if is equal to -1, then you can say that it is not reachable, right?
Label, yeah, correct. So yeah, correct. Label, if it is not reachable from source, that then label will be -1. So that for that you can also check. Otherwise, after this while loop, definitely you if that list will remain empty and you can check later. Yeah, so this is the solution for the problem number 1. Okay, this is the simple solution. So if anyone have any doubt in this to understand, so what we are doing, I'm again repeating the code. So what we are setting, this v equal to end. Okay, so end is a vertex where we want to actually traverse. Okay, and
Sir, you
this
can
is just
remove
a,
I from there.
sorry.
I is of no use. You can remove that.
Okay, so that I can remove. And this list actually we are maintaining for the path. How many vertex are there in the path? And we are using this while loop. So while parent of v does not equal to -1. Okay, so this -1 means we are starting from end. Okay, so you can see we are starting from that end vertex and we are checking the parent for that vertex. So we will repeat this process, and for source vertex actually we will get this -1. At that time our while loop will terminate. Okay, so as I explained in the notepad, we will start from the end vertex and we will check what is the parent for that vertex. Okay, and we will append that parent vertex in the list, and we will update this vy equal to parent of v. Okay, so this v value we are updating by the parent of v, and this value will run repeatedly. At after some iteration it will reach to the source, and at that time we will get the parent of source equal to -1, and then this loop will terminate.
Sir,
Yes.
why we need label?
So label is not useful in this problem. Label is basically returning the value like so actually we are
But
getting this traversal tree. Okay, so label is just representing that this if we are starting from source, this node. Okay, so yeah, this source vertex. So label of the source is -1, and what is the next label? So what is the neighbor label actually we are calculating? So this is 0, or if we are starting from 0, so this will be 0 and this will become 1, and the label for the next is this is 2, and this next label is 3, and this next label is 4, and this next label is 5. So this is representing the label information, neighbor label. Okay, but this is not useful in our problem. So, but our algorithm is actually returning this information, so you can ignore it. Okay, So I hope this problem is clear to everyone. The solution code. Any query in this? Any doubt? Okay. Then I'm moving to the problem number 2. Okay. And also one thing, these problems are not random problem. These problems which we are giving in the this coding session, these are actually previous OPP problems. Okay, so not all, but many problems are directly taken from the previous OPP exam. Okay, so do not ignore completely. So these problems are also important for the practice of the OPP exam. Okay, so you will get similar type of problem in the OPP exam.
Sir, can you suggest how to practice on lead code?
A lead code I have already mentioned in the first session. So according, I think TA is also discussing some problem on the lead code, correct? If you have joined the TA session.
No, sir, I didn't go to the TA session.
He is doing it every Saturday.
Yes, so one session actually TA is discussing previous year question, that theory question, and one session TA is discussing some problems from the lead code. So I think you should join that session to get some idea.
Okay, sir.
Okay, Saturday I think that session is from 5 to 7.
Thank you, sir.
Okay. So write a function. This is second problem. Write a function back and forth. Okay, this is also one previous OPP problem. I remember that. So back and forth, a list. So same things. We have adjacency list, and one and two. Okay, these are two vertex. To return the maximum number of possible route between node and one and n2. Okay, so now this problem is directly given in the terms of graph, but the same scenario can be created on the real life stories, like you have given some map or you have given some real destination names, and you want to figure out that if you have some groups of people and they want to just move from one source to destination by the different possible path, okay, without using any common medium vertex in the path. Okay, so what are the possible paths in the route? That so same things, the problems can be designed on the same concept. So to return the maximum number of possible route between node n1 and node n2 in the undirected graph without going through the same node again, with exception to n1 and n2. The connectivity details between nodes are provided by the adjacency list A list. Okay, so what this problem statement is saying, I am explaining by the graph. So this is the input graph which is given for one input. Okay, as a adjacency list. Okay, and with this input we have another information, this 2 value. Okay, and this graph we have created for this adjacency list. Okay, so this is undirected graph, and here these are the another 2 value, and one is 0 and 2 is 1. So I'm noting down this, and 1 is 0 and 1 and 2 is 1. Okay, so these are two vertex where we need to figure out the different possible path from 0 to 1. But in path we will not repeat the vertex. If we have used any vertex in the one path, we will not use that vertex in the another path. But these are actually starting and end vertex, so we will not consider this, okay, for the repetition. So in this graph you can see this is a, like suppose this is source and this is a destination, and you need to figure out the possible path. So I am noting down the one possible path. You can randomly check. Okay, so suppose if I'm reaching from 0 to 1, so there is one possible path you can see from 0 to 6 and 6 to So like I'm noting down this part. So 0 to 6 and 6 to 1. So this is one possible path. And second possible path, but we will not use 6 node again in this next path. Okay, but definitely the source and destination will come in the path. Okay, so we are ignoring this. So now second possible path you can see, if suppose if I move from 0 to 3 and 3 to 1, we can do this. So this is another possible path, 0 to 3 and 3 to 1. So like, okay, so this is another. Okay, so now next, so third path. What are the other possible paths? Now we have used this 6 and 3. Okay, now we can not use this 6 and 3 again. And what are the another possible path? So now another possible path you can see, if we move from 0 to 2 and 2 to 4, then 4 to 5, and then 5 to 1. Okay, so this is another. So 0 to 2, 2 to 4, and 4 to 5, and 5 to 1. Now this is the, now you can see all vertex are used. So we have total 3 possible path. Okay, so for this, where we are not repeating any internal node in the past. So answer for this problem is 3. Now how you can do this? And one code is already given to you, and problem statement. Okay, so we open this. So main code you can see. So here one template code is given. You can modify this code. Okay, so here instead of using the same as it is, you can modify this, because in the logic some modification may be required in this. Okay, this is the same similar very similar code for the previous code. Same things, we are just maintaining in this code. Actually we are maintaining this visited information also when we are traversing using the BFS algorithm. So we will also traverse, we will also maintain this information which node is actually visited if we are applying this BFS algorithm on any source vertex. So that information we are getting, label information it is not given in this, but parent information again we are maintaining this code. Okay, so now write the solution code, and you can also use this code, and you can modify this code. Okay, and on the portal this code is actually configured as a template code. You can modify. Now just tell me the logic, how you can use this, and what logic you can apply. So I've explained the problem statement, and I've also explained the input output, what is the output, and how you can figure out the logic. Any idea, anyone?
So I think every time we need to check whether the next vertex is visited true or false. If it is visited true, then we should not visit that. We go for the other one. I mean, I'm thinking that way.
Okay, yeah. So this is very close. Yeah. Any other?
Sir, you can use the neighbors of the first vertex and then do the BFS from that.
Mm-hmm.
And if it's visited, then you can count. Actually, it passed. You can check my code.
Okay. So here actually, if I'm asking one thing, is this parent information required or not?
No, visited is required.
Only visited is required. Okay.
Yeah.
But how you will identify that mediator node in the path?
No, I will start the BFS list path from the neighboring nodes of the start end one.
Okay, so let me just explaining your code. So this, suppose if you are starting 0, okay, and you apply the BFS on 0, and what this BFS will return the information. So how you can use this information?
No, I will not start from 0. I will start from 2 or 6 in this figure actually. Because
Okay.
if the neighbors of the
Okay. So you are applying this on the neighbor of 0, correct?
yes,
Neighbor of
and
0.
yeah, if the end one is 0, then I start from 2, 6, and 3, I guess. The neighbors of 0.
Okay, that
And check
shows
whether
this end one.
the
Okay.
N2 is available on the BFS return visited. And then if it's there, then I increment the count.
Okay, but suppose if you are applying this BFS on 2 and BFS on 6. So these are BFS. So it will provide the information of visited or parent information. So after that, what you are trying to do?
I'm checking whether N2 is in the visited.
Okay. So suppose and 2, yeah, for both actually N2 will be visited. Okay. So from 2 also and 6 also N2 is visited. Now true this also. Then how you are figuring out the number of path?
I increment I mean I have a variable path count which I increment by 1 if it is visited.
Okay, so here actually you can see I'm just applying random your logic on the graph. So from 2 also we have this one is visited, okay, and 6 also this one is reachable, correct?
Yes.
From both actually this one is reachable, so you will get definitely this 2 for and 2. Okay, so now you incremented this like 2. After that,
Then again 3 is there, right? So I'll visit 3 is the neighbor in this, right?
3 is the neighbor of 2.
0, 0, 0.
Okay, this is
I'll
another
just,
neighbor. Okay,
I mean,
so
you have to think of the graph, right? I mean, the
uh-huh.
one. So then again, I will try for 3, whether I can reach it from 3.
Okay. Okay. So you are again trying from, but there is a possibility that you are reachable. Okay. Suppose if you are applying from the on the 3 and again you will get true. Correct?
Yes.
Okay. This is fine. So you are getting 3 answer for this. Okay. But suppose let me. I'm just creating one input. So suppose this is 0, and you have applied like 1, 2, and 3. Okay. And after that 4, 5, and 6, and 7. Okay. Suppose you apply the same things on here, and we are and one you are taking this one, and two you're taking this one. Okay. Now, if you apply this same logic on this, how many
Hmm.
answer you will get?
I'll get 3.
3, no? But if you are suppose if you are taking one path, so like 0, 1, then 5, then 6, then 7, then there is no other possibility of the path without repeating this 5 and 6. Okay, you cannot repeat this. If you have already taken in one path, you cannot repeat. This should not
Okay.
come. Yeah, so this is not correct. Yeah, but you tried. This is very nice. Okay. Okay, any other logic? So as I asked in the previous, so this parent information is required or not for this? Okay. So I'm giving the hint and logic for this. So same things. What happened? Actually, BFS algorithm is given. Yeah, that is fine. And what we can do? So we have given this end one and end two. Okay, so this is end one and this is end two. And what we can do? We can apply the BFS on this zero. Okay, so BFS on zero, and this BFS will return all the true that visited vertex. Okay, and after that we will check this n2 is reachable or not. So if we are getting visited n2 is the true, that means it is reachable. But so BFS actually algorithm will provide the shortest path from 0 to 1. When you apply this BFS algorithm or first time on this 0, it will return a shortest path from 0 to 1. So suppose for shortest path, it is giving this path like 0 to 3 and 3 to 1. There is no direct link from 0 to 1. And suppose if you apply that BFS, okay, so 0. And after that, what are the neighbors for this is 2, and next is 3, and next is 6. Okay. And when we apply, when we check from 2, so the neighbor of this 2 is 4, which is not visited. Okay, and from 3 you can see we can move to 1. Okay, and from 6 we can move to 5. So yeah, this is the traversal for the BFS. So this is 0, and when we apply the first time, so you can see we are getting one path from 0 to 3, 0 to 1. So this is uh, 0, then 3, then 1. Okay, so if we use the parent list of the first traversal, then we will get this path. Okay, and what vertex we have used in this? Okay, so what are the that mediator vertex which we have used is 3. Okay, this is 3. And what we can do? So after getting this first information, and we have already this BFS algorithm given in the code. When we apply the BFS again on this in this code, okay, so after getting this first path, we will apply the BFS algorithm again on 0. But second time, we will maintain a list. After getting the first information, we will maintain a list what vertex is already visited in the previous runs. Okay, and in this BFS algorithm, at the time of checking of the neighbors, when we visit the actually nodes from the any neighbors, we will also check this previous record. Okay, so what intermediate vertex is already visited, okay, in the previous algo or that code. Okay, and then we will ignore this. If any vertex is coming in the previous visited node list, then we will ignore this. Okay, we will not visit it again. So what happened? Suppose if we are maintaining this list, if we have used any vertex in the previous path, so we will apply the again. Okay, so same things, we will apply the BFS again. So from 0, now we will check what are the neighbors of 0. So neighbors of 0 is 2, 3, 2, 3, and 6. Okay, but we will check all neighbors are exist in previous list or not. So we will only consider the vertex which are not in the previous visited list. Okay, so we will check we will check this 2. 2 is not exist right now in this previous visited list. Okay, so we are maintaining this previous visited list, and we will consider that 2. Okay, now next neighbor is 3. So 3 is already exist, so we will not repeat use again. Okay, so we will ignore this. And next is 6, so only 6 is there. Okay, now this is the 2, and after that 2, same things we will repeat again. So from 2 you can see 3 and 4 are connected, but 3 is already exist in the previous list, so we will not repeat again. So 4. Okay, and from 2 there is no possibility. Okay, so, and then 6 you can see we are reachable to 1, and from 6 we are also reachable to that 5. Okay, so now all vertex are done, and we will ignore the 3 in this process completely. So now the another path what we are getting, if you suppose apply the same parent reverse path things, so we will check from path from 1 to 0. So you will get this information. So 1, then 6, and then 0. So you are getting another path. Okay, if this one is reachable from this. And we will also note down this. Now 6 is also used in the path. So we will append this 6 information in the previous visited list. Now this is now 3 and 6. Okay. And again, we will apply the BFS algorithm on 0. Okay. So this time 0. And we will not use this 3 and 6 when we are applying this BFS algorithm. So 0, what are the neighbors of 0? Again, 2, 3, 6. But 3 and 6 we have already used. Okay. So we will only consider 2. Okay. And from 2, we have neighbors 3 and 4. So 3 will not come, only 4 will come. Okay. And from 4, only 5 is there. So 5 and 3, but 3 again we will not take, only 5 will come. And from 5, 6 and 1 is there. Okay. But 6 is exist in the list. So 6 will come. Not 6, sorry, 1 is come. Okay. So when you apply the BFS again, and after ignoring these vertex, so you are getting only this path. Okay. And you will consider this as a third path. So 0, 2, then 4, then 5, and then 1. And this one is still reachable. So because of that, we will consider this path. Now, after this, we will include all the vertex, this 2, 4, 5 in the list. 3, 6, 2, 4, 5. Okay. Now, again, we will try to apply the BFS algorithm logically on the 0. But this time, when we apply the BFS on 0, so the neighbor of the 0 is 2, 3, and 6. But all are actually exist in this previously visited list. Okay. So that means no neighbors are available from this. So we will not consider any neighbor to traverse. So that means this is disconnected. And you will get the -1 information. That means false value for the minus that one vertex. This is not visited. After when you apply this BFS algorithm on 0, this false will remain same on the 1. This is not visited. At that time, you can stop your process. That means now the 1 is not reachable. So during this process, you can just note down that how many paths you are getting. Okay, when you are repeating this process. Okay, so we are getting this 3. So what modification is required, and how you can write? So 3 things are required. One is you have to maintain this previous visited vertex in some place. Okay, and some modification is required in BFS algorithm. So that means during the that BFS algorithms, so where you can do the modification. So like first things, you have to store some previous visited vertex, and you have to pass that list in this function. And inside this function, you can see this line. Okay, when you can see where this is the part where we visited the vertex, visited the neighbors of actually. So for k in a list j, so what are the adjacent of j? We will read in k. If this k is actually not visited, so you can see if not visited k. If this k is not visited, then we consider it as a visited, and we note down the parent. So here what we can do, we can also add the condition if this k is not exist in the previous visited list. Okay, so that if we will add this condition like this. So if and k not in, okay, so that previous list, what list we are taking, so like previous PRV visited. Suppose this is the name of our list which we are maintaining. Okay, so this we will consider one more condition in our code, and this list we will consider as an input for this. Okay, now we will add this. So this is the modification which is required in this BFS list path. Now this BFS will always provide the new path actually. after ignoring this previous visited node. Now, apart from that, this is the modification. Apart from that, you need to write the code for the path. Okay. So after getting the path, you can figure out the node which are actually traversed. Okay. Which are actually we have figured out in one path. After that, just ignore that. Ignore the nodes in the path which you have already figured out in one path. So that you have to maintain. So that means that parent path calculation code is required for this. Apart from that, only you need to just figure out that this call things. You have to just call the things after that counting the path. You need to write the code for that. Okay, so this modification I have already done, and after that just write the code for to calculate the path and count the path and call this function accordingly.
Sir, can we do one more thing? Means another way.
Yeah, please tell me.
Sir, so we can, instead of using BFS, we can also use DFS, and we can suppose 0 has 3 neighbors. So we will apply 3 times. We will apply DFS 3 times on 0 and check if it reaches 1 from all its neighbors or not.
Okay, so DFS you are trying to apply. Okay, so let me check. So you are deciding based on the neighbors, correct?
Yes.
Okay, so this is A, and this is B, this is C, this is D. Okay. But still, you have to. Okay. So.
Sir, may draw another level. Draw another level.
I'm drawing. So B, C, D, E. So same. I'm drawing again. So E, F, G, like this. So suppose if you're applying the DFS, and you can figure out the path.
So now what we'll do
but
is,
DFS is actually not written the shortest path things like this.
Sir, but we don't want shortest path, right? We just want how many times means how different ways we can reach there.
So suppose if DFS written one possible path like A, then B, then E, then F, then G. Okay.
G. And after that, we'll
Like,
suspend B and we will go for the C. And we'll use DFS again on C and then
so,
again on G.
okay. So same app. That means you want to do the same process, but you are only changing the BFS.
Yeah.
That BFS to DFS. Okay. Yeah, you can try. Let me think. Any possibility if DFS will not work or. Okay, so DFS is actually checking the false. I think that DFS will also work. Yeah. Because reachability we can also check with the DFS algorithm. So, and after removing this, if you are not reachable to this G, definitely you can stop the process.
So, sir, what we'll do is we will look at the A list and we will look at the neighbors of our end one, and then we will apply DFS on all the neighbors.
Yeah. All the neighbors. Okay. Yeah, you can apply the DFS on the neighbors. Yeah. Or why you need to apply the DFS or all neighbors actually? You can apply the DFS on the same source, no?
Sir, but how would we know how many times we have to apply?
You can run a while loop. So if you're doing the same process, so you can use a while loop, okay, and check if you are reachable to G or not. And at any time, if you're not reachable, if you're getting this visited is false, then you can stop the process while loop.
Okay.
So same things we actually want to do here also. So we are applying this BFS algorithm on A, and we are finding out that this G is reachable. Okay, and after that we will figure out the path by this parent information. So then we are figuring out that what nodes actually are coming in the path. Then we will mark as a that visited, and we will not use again. And again, we will apply the same BFS algorithm and we will check this is visited or not. So that means if this is visited after ignoring the previous vertex, visited vertex, so that means another path is there. So then we will again figure out the path by the parent information and we will note down this. So same things you can do with the BFS algorithms. So no need to apply the BFS on all three neighbors. Maybe after one, you can just stop the process if this is not reachable. So if you are using while loop, so while loop will terminate after one. So you will get the path after one. Okay. And after that, when you apply the second time DFS on A, you will not reachable on this G. Then your code will terminate at this point. Okay. But here actually, why you want to try BFS, but code is already given for the BFS. So why you want to increase your work? If
Sir,
code is already
actually,
there.
sometimes BFS becomes complex, and for reachability, I think DFS is much better than BFS.
No, but it is given now. So why this is complex? That code is given. And if you remember the DFS code, you can write. Yeah, definitely this code is given in the template. You can ignore completely and you can write the DFS code completely. But still you have to apply the same logic. Okay, after writing the DFS code.
Yes, sir.
Okay, but yeah, additionally you can try your approach is working on the problem or not. But here BFS code is already given, so you can just save your time. Okay. Okay. Any query in this logic? What we are trying to do here? How you can write the logic for that? Anyone have done? Okay. So one have submitted. Yeah, Prince, are you there in the meeting?
Yes, sir.
Okay. Have you done submitted?
Yeah, I've submitted, but I'm not
Okay. Okay.
sure. I mean, I'm just trying to figure out the logic you said. I submitted again, just checking the
Oh,
code.
test case is passed or not?
Yeah, test case passed. That earlier also passed, but your logic I'm trying to implement. I mean, it's
Oh,
okay.
okay, but you did not understand the
I
logic.
understood. I understood. I implemented that also. I'm just because test case is not failing, right? I'm just trying to
Okay.
revisit and see whether it's working.
Okay.
Test
Okay. Okay.
cases
Yeah,
are
fine.
passed.
Okay. Okay. Yeah. Just try to figure out. Okay. So meanwhile, I'll also writing the code for this. So I've done one modification in the BFS. Okay, so this that previous, so I'm writing completely. So previous visited. Okay. So main function we have to write is this back and forth. Inside this function, we will maintain this list. So previous visited list, and this list is initially empty. Okay. And because we need to return the count. Okay, so how many paths are there? So that counter we will use. So like count path equal to 0. And so here, okay, so we will call this BFS algorithm from this function. Yeah, okay. And we will note down this visited comma parent equal to this. Okay, so this BFS list path, and we call this main algorithm, which is given already in the code. And we pass this all information. Okay, so a list v. Okay, so this v is not there. So what we should pass is end one point. End one. Okay, and previous visited. So initially, first time you can see this is empty. So that means our algorithm is running on the main input graph without any updation. Okay, so on original graph. And after that, after finding the first information, we will run the while loop.
Sir, but previous visited is a list and the function has n2 is a integer, right? So it won't take it as, oh, it's previous visited. Okay.
No, this is not defined as an integer anywhere. So
Yeah,
what we
you
are
can
passing here, we are passing list. So it will consider as a list, the
yeah,
code.
you can do changes.
And here we are using this k not in previous list. Previous visited. Okay. So this is the first thing. And after that, we will run this while loop for if we are getting the this visited value for n2 equal to true. Okay, so what we can write here, so we can write the visited information. So visited and visited for n2. So this is our target. If this is true, okay, then we will repeat this process while loop. And inside this, if this condition is true, that means we have another path possible. Okay, so if we are getting visited of n2 equal to true, so that means one path is possible. That means we will increment our count here. So path count path plus equal to y1. Okay, now this is the things, but after that, this is the main part. We have to figure out the path. Okay, so we know that we have one path, but we have to find out the possible vertex in the path. So that means we need to figure out the all list of the path here. So what we can do, so we can take one list, empty list, or what you can do, you can make separate function for this. Otherwise, you can do in the same. Let me just do the same. Okay. Current equal to, okay. So yeah. Okay, one second. This is path. And this path, actually we will note down the vertex which are coming in the path. So what we can do, we can take like C current CO double R current equal to what is the current vertex we have. parent. So we will like this parent. So what dictionary we are getting? Parent here. And for parent, we will use this like it's a and two. Okay, so this is hmm. So for you know that we start figuring out the path from the last node. So this is n2. Okay. So n2 we have, yeah, n2 we have, this is the source vertex. Current. So what is the first parent of this n2? We are noting down this, and after that we will just run a loop. So while this CURR current vertex is not equal to the source vertex. This source vertex means and one. Yeah. We will repeat this process, and every time we will append this path dot append into this CURR. Okay, this is done. Why this is given undefined name build state. Okay. So now what we have figured out here, so after getting this information, that means our N2 is reachable from N1. Okay, so this information we are getting this BFS list, and we are incrementing our count path, and after that we are getting this information what vertex are coming in this path. So we are traversing from end vertex. Okay, but N2 you can see we are not including in the path. So this time we are only focusing the vertex which are coming in between the path, not including the source and vertex. So we are starting with this current vertex, which is actually a parent of this N2. Okay, and checking that this current is not equal to N1 source vertex. If this is the true, then we are appending this current vertex into our path list. So that means this path list is actually containing the mediated node of the path, okay, which we are getting. After getting this information, what we can do, we can add these vertex into our main previous visited vertex, this one. Okay, inside the main first while loop. Okay, inside this, we are doing all these things inside the while loop, and we will use this dot, and we are actually this previous visited is also a list. So we will not append here, we will extend. We are just adding the nodes which are coming inside the path into this previous visited. So extend, and we will just pass the path. Okay. So that means all vertex which are coming in this path will be added into the previous visited list. And next time we will call the same algorithm again from here. So visited parent, and same thing, you can see we are passing again and one. Okay. And finally, so this is done, and after that we will return the main output from the function. So return path count path, sorry. Okay. So yeah, this is done. Okay, so you can write the comment here. So okay, so let me test this. Okay, so that means our code is, I think, running in infinite loop. Failed. Okay, what is the issue in this code? Previous visited equal to empty. This is second, fourth, and this is we have done here. So if not visited and k not in previous visited.
Sir, this problem, like whenever we are practicing and whatever problem will be there, will is always use this adjacency list or matrix representation in the problem.
It may be anything. You
Okay.
have to write the code based on the input.
Mm-hmm.
Or you can, what you can do, you can also make the adjacency matrix to the adjacency list if you're comfortable.
Mm.
Okay, so you can convert. Why this code is actually failed, and figure out this. Previous visited, we are maintaining one list. Count path is equal to 0. Visited parent, we have called the above function a list and one is the source, and one is the source. Okay, the previous visited. While visited of n2, so while visited of n2 equal to true, so this is fine. N2 is our so destination. Mm, count path, we have increased path. This is the empty list, and current equal to parent of n2, and while current is not equal to n1. Okay, so in path, I think we have not updated the current value inside this while loop. So this while is running infinitely. So we have to update this CURR equal to parent of. These things we have missed. Parent of CURR. So inside this while loop, when we are appending the current node in the path, then we will update this current value to the parent. Then we will check the their parent. Okay. So let me run again. Maybe this should pass. Yeah. Okay. This is working now. Okay. So now previously visited, we are extending all the nodes and then again calling the same function. So this will return a new visited dictionary and new parent dictionary after ignoring this previous visited node. Okay, then we will repeat the same things again in the while loop, and we will repeat this. This is the solution. If anyone have any doubt or if you have done anything else, you can also share. Any query in this? What we are doing in this code? Any doubt?
So no doubt, but in general, I personally feel that week 4 onwards, the complexity or the depth of understanding need to be more actually.
Yeah, because of that, just trying to finish all algorithm first when you are trying to solve the problem. Okay, so do not directly jump to the problem. Just come first, understand the algorithms of the week. So that basic algorithms, at least you should know this BFS, DFS, and topological sort, and the some version of this BFS, like when we are also getting this parent information. So this understanding of these algorithms should be very clear if you are moving to the problem. After that, you need to just figure out the logic, how you can use this. So here, what we are doing, we are simply finding out the path. So path, this problem we have already discussed in the previous problem, you know. Okay, so how we can figure out the paths by reverse, by the backward process from so destination to source. So same information we are using here. Okay, same code we are using here by repeating this process. So actually, after solving some problems, so new problems is actually comes as a superset of the previous problem. So if you have already solved some part of the problem, like in the previous problem we have discussed this path calculation, then in this problem this is used again. So same thing. So if you are solving many problems, so the new problems you will get that the new problem is just a little bit superset of the previous problem. So just practice on that. Yeah, first time definitely you will feel that yeah, complexity is high. Yeah, definitely these are graph algorithms where your logical understanding should be good and your imagination should also be okay. So to understand this graph algorithms, because here actually everything is stored in some dictionary and this nested list in the adjacency matrix, but we have to think logically in the graph form how these algorithms are working. So that both things, imagination and code understanding, should work at the same time.
True. I think you need to practice a lot, then only it will come.
Yeah, yeah. Because of that, we are giving many type of scenario. So here, if you know this, how we are calculating the path. So in later week, this will again come in some problem. So now you have already done one time, and if you already understand that, you can utilize this in the next problem. Okay, so please just apply the dry run on the algorithms by paper on pen. Okay, so just take some any random graph and just apply how the algorithm is working. So that dry run is very important for this. Instead of just trying to learn the code, this is very difficult for this course. You cannot learn the code for like 30 or 40 algorithms. You cannot learn, and nobody can learn actually. But you can, if you know the concept, if you know the understanding of the dry run, how the algorithm is working, then you can write the code. If you understand the steps, then you can write the code by your own. This is easy for this course actually, but you cannot remember the code which you have already learned sometime before. You cannot remember as it is.
So, any suggestion on like to have a better grip in this? What I do is like if I don't understand the code, maybe I'll take this into some ID and try to analyze, add a debugger and try to analyze. But that also have some limitation. Like it will not tell all the details of that what is happening in the code. Any generic logging mechanism like any logger API or anything is there?
No, if you want to understand the step-by-step things, you can use this Python tutor, that where you can see the update on every step. And because of that, we have added this in our GitHub notes. Let me open this index.
Sir, I tried the DFS one. It is working.
DFS is, yeah, it will work. I think the same logic, na?
Yeah, sir, same logic. Just I used it on the I used DFS on its neighbor, and the code is very small for that. Just the one thing I had to do is copy paste the DFS thing. It was very big.
Okay. That DFS algorithm, na? You have to copy that.
Yeah.
Because of that, I asked that if BFS code is already given, why you are writing the another.
Yeah, sir, but because of DFS, actually the main code that was back and forth, it became very small. It was very small.
Okay. But I think, so yeah, you can share. Okay, let me just explain this. After that, I'll check your code.
Yeah.
So because of that, we have added this Python tutor thing. So I think it is added here or not. BFS, yeah, this thing. Okay. So to step-by-step execution and what happening in the data, that data structure which you are taking, like this visited, that queue, you can see all the steps here in the step-by-step. So in this okay, queue, what this is initially queue when we are running the code. Each step, what updation is happening. Okay, so you can understand that how the algorithm steps are working. If but initially you should understand all these steps on that logical graph on paper and pen.
Okay, so first we have to understand the algorithm in kind of
Uh,
paper and pen, what is happening.
yes, just
That
take some graph image and just apply the steps when, by the paper and pen. Okay, and how this that traversing is happening. Just understand first things that, and then after that, if you understand all the steps, just trying to write your logic to perform that. Okay, so
okay,
that
yeah.
is actually very good. Okay, yeah, so let me check the code, the DFS code. Yeah, what's your name?
4661.
Okay, same. Okay, so this is column 2. Okay, so first thing, this is stack and this is list. Okay, DFS, and after that you have done this. Okay, so back and forth. Okay, you have applied number of paths. Okay, you have done the same thing. So apply the in all neighbors you have applied,
Yes.
and check if visited and two number of paths is equal to 1. Okay, I think this will also work for the BFS. This should also work for the BFS. Okay, we can apply the BFS on each neighbors.
Sir, the same thing.
I think we can do.
Can you try that?
So that let me check. Because you will always get the path from the different neighbors, because neighbor we can also not
Yeah.
repeat. Okay, so that logic we can use, but here what I'm thinking that this is doing some extra task. Okay, how this is doing some extra task, the complexity is increasing. So like suppose in this case, uh, suppose this is the 0 node, and suppose we have 5 that neighbors of this 0, 1, 2, and 3, then 4, then 5. Okay, and after that we have one common path for all. Okay, then 6, then 7, like this. Okay, and we are just checking the path from 0 to 8. So what your algorithm is doing, your algorithm is applying DFS on each, correct?
Yes, sir.
Like this. So after, suppose if you are applying DFS on this, you are getting this path, and after that there is no possibility of the path, but still your DFS is working on this again, 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 and again, 4 times.
Yes, sir.
Okay, so I think this is increasing the complexity of the code. But in
Okay.
our code, actually, if we are applying this DFS first time on this, and when we are applying the second time DFS, so you can also do this modification. You can just break your loop. Okay, so suppose if you are applying this DFS on second time from this, but there is a chance you cannot break. Yeah. But suppose if you are not getting path from this second word neighbor, then yeah. Okay, so yeah, in our approach, actually, we are getting the path from here. Second time when we are repeating, so this will not be reachable. At that time, we will stop the process. So only 2 call will be there. But in your code, definitely all these 5 calls will be happening. But logic-wise, your code is also fine. and this our BFS will also work, I think, for the same. Only the complexity is higher. So where is your code? This is your no?
Yes, sir.
Yeah, this is your. Okay, so let me check this. So this is a comment. So let me just not. I'm not updating this. It is working. But the same the things is this is running. This is depends on the number of neighbors, and it will call for each neighbor. Okay, so this is just the change. Otherwise, logic wise, it is fine. Okay.
Yes.
And we cannot. We can also not break this. What there is a possibility that suppose if we are getting this visited and 2 is equal to false, and suppose we are breaking at this point, so there is a possibility that we are not reachable from that node, but there is a chance that we are reachable from the another node. So after that, we cannot break this. Yeah, but logic wise is okay. Okay, that this is fine. Okay, so any doubt in the anyone in this approach? BFS, TFS. Okay, then move to the third problem. Uh, if someone is raising the hand, yeah, Preetadeep.
Yeah, good evening, sir. Can you hear me?
Yeah, yeah.
Yeah, sir, could you add me to that live coding team? The only live coding team I see is PTS September 2021. I don't see the
So
new one.
you are doing this course this time?
I'm repeating it for improvement, sir. Yes.
Okay, improvement. Okay, okay. So if you have the calendar link, so that Replit
Mhm.
that invitation link is already added in the calendar. So I'm sharing in the chat. 1 second.
Okay, got it. Yeah, got it. Thank you, sir. Yeah, I have
Yeah.
taken it from the calendar event. Thanks. I was looking
Okay.
at it from Discourse, but yeah, that was not an invite as such. Got it, sir. Thanks.
Okay, okay, okay. Yeah. Okay, so now moving to the third problem. Problem is third. 3, 4. Okay. Okay. So this is the third problem. And just I'm reading the problem statement. A group of workers have to complete a list of tasks. Those tasks have dependency within the task list, but the workers prefer some interesting task and hates to do some boring task. They always do the most interesting one among the available tasks to be done. Okay. So write a function pool worker and a list and preference. This two information is given. A list is the same dictionary adjacency list, and what is this A list actually? So to return the order in which the task will be done. A list is the adjacency list with the dependencies. Okay, and preference is the task sorted in preferred order, in which task in index 0 is the most preferred, and this index -1 is the last. Okay. So here preference are given for the task, and some dependency is given. So that dependency, what dependency is represented, uh, okay, so that means you can see the graph. So that means you, for two, the second task, you have to complete the zero task first. Okay, to complete this second, third, and one, you cannot do this task second, third, and one without doing this zero task. Okay, so this is the dependency, actually it is given. Okay, so you can see this 1, 2, 3. Okay, so 1, 2, 3, these tasks are dependent on the zero task. So you have to complete this zero task first, then you can do this 1, 2, 3. Okay, so all the dependency you have to complete first. But among these dependency, again, you will prefer the task based on this preference list. Okay, so after zero, suppose if you done this zero task first, then you have you can do this second and third, or not third. Okay, so because third is also dependent on second task. Okay, so let me just take this example and explain that. Okay, so this is graphical representation of the dependency, and some other information is given like this preference list. Okay, so this information is given. So this adjacency list is just a representing a graph. Okay, this is directed graph. So 0 to 1, 2, 3 are connected, directed. Okay, and this is representing a dependency. And I'm telling you, if you are getting any problems where the dependency are given, okay, so any that task is dependent on the another task, and so that problem is basically a that directed aside DAG type of graph. Okay, so that means some DAG graph is given to you, so that DAG, okay, directed acyclic graph, and you can think about this topological sort and longest path in this DAG. Two algorithms which we have discussed in the Week-4. You can think about these algorithms. Okay, and the question is also very important. Many questions are asked in this exam also, that quiz one. Okay, so this topological sort based question actually generally comes. So what you can think here, what information is given. So let's, first things we will check which task we can complete first at the first time. Okay, so we will check the vertex which have actually no dependency. So you can see there is a multiple possibility here. So like you can see 0, there is no incoming edge coming on the 0 vertex. So that means 0 we can start. But is there any another node where dependency is not there? So we can see 2, but 2, one incoming edge is coming. Okay, so incoming edge means it is dependent on any another vertex. So we cannot do this. So 3 is also, we cannot do this. 1, 4 is also there, 8 is also okay, 5, and this 6, 7. Only we can start with 0, because 0 there is no incoming edge. That means 0 is not dependent on any but another task. So this is the first things. But when we complete this 0, so that means we will finish this. So this dependency is also removed. Okay, so 0, this was dependent. That means 0 was the this 2 is dependent on 0. So now 0 we have done. So this means this is now removed. So the what are the outgoing edge from 0 that will remove actually. Okay, so this edge will remove, this will remove, now this one. Now after doing this 0, what are the possibility we have to do next? So this 2, you can see after removing this edge, now 2, there is no edge, incoming edge on the 2. So 2 we can do, and 3, but 3 we cannot do because there is a edge coming from the 2. Okay, so now this is not, and 1 is still, after removing this edge, still 2 edges coming on this one. So that means we have only possibility for the next task is 2. We can, so if we have no choice, we will do this. Okay, so after 0 we will do this 2, but when we complete this 2, another this 2 edge will remove. Okay, so now 3 is free. Okay, there's no incoming edge on 3, so that means 3 is available. And okay, so no other vertex are available free. Okay, so that means we have to complete 3. Then after 3, then these 3 edge will be removed. Okay, so you can see now we have the choice here. Okay, so after 3 you have two choice. 4, now this 4 is no incoming edge, as well as 8 is also not no incoming edge. Okay, so we can do both, because now it is not dependent on any. So 4, and but this 1 is still have dependency on 5, so we cannot do. But now here, if we are getting choice, so now after 3, which task should be done next? So 4 or 8? So now this, in after getting this situation, we will check that which task have the higher precedence. Okay, so 4 or 8. So you can see this preference list and which task is coming first in this. Okay, so you can see 8 is coming first, after that 4 is coming. Okay, in the index wise, so 8 is coming before the 4, so that means 8 is most have the most preference. So we will select this 8 next. Okay, we will not select the 4, so 8 will be selected next. So this 4 means this is boring compared to the 8, so 8 will be selected. Now after selecting 8, this edge will be removed. Okay, now there is no choice, next choice, so we have to move to 4. Now we have to select 4. Okay, and when we select 4, these two edge will be removed. Okay, now this 5 is free, so we have the choice for 5. And any another vertex we are getting free? No. Okay, yeah, so that means we have to do this 5. And after 5, when we do this 5, now this 1 become free, and this 6 also become free. Again, two choice, 1 and 6. Okay, so now which one should we do next? So that means you can see 1 is most preferable compared to this 6. Okay, now we will move to the one side, this one. Okay, not this. After 1, and then again we have no choice, then we have to move to 6. And after 6, only 1 remaining, 7. So that is the sequence. Okay, so that means your order should come like this. So 0, 2, 3, then 8, then 4, then 5, then 1, then 6, then 7. Okay, so this should be the output of your problem. So if you see this, so sample output, let me compare this. So 0, 2, 3, 8, 4, 5, 1, 6, 7. Yeah, we are getting correct. So this is the problem. And now if you have already done this topological sort, then you can do this.
Sir, so basically we have to use the topological sort, and while topological sort, the vertex which has the same degree, we have to look at the preferences.
Yes, yes, yes. This is the modification you need to do in topological sort. Okay, so when we are applying this topological sort, just update this information. If you are getting the vertex more than 1 with 0 degree, at that time select only the vertex which is coming first in this preference list.
And sir, suppose if there is no preference list, we can go by our choice.
Yes, then you can go by your choice. So that means that there is multiple order possible then.
Yeah, yeah, yeah.
But here in this case, only one order is possible.
Okay.
Okay. So now you can use this topological sort algorithm. If it is not given in the code, we have to write complete by your own. Yeah, you have to write by your own. It is not given. And this problem is also from previous OPP exam. Okay, anyone have any query for understanding this problem or any logic wise? And any doubt in topological sort if you not know what is topological sort? Just give me 2 minutes for me. 1 second. Yes. Okay, anyone have done?
Yes, sir.
Okay. Prince? Okay. Okay, I'm opening your 1 second. Problem number 3. Yes. Okay. And this is working. Fine. Yeah. So, Prince, can you just explain your code quickly?
First, create the integers of each of the nodes, and then I append the vertex which is at the 0 vertex, which has integer 0 to the cube.
Okay,
Then I create
so
the preference index so that I can sort it later using the index key.
this is preference index. So you have created the dictionary.
Dictionary.
Okay,
So
based on
that
this okay key. Okay.
then every time I go inside the queue, I sort the key queue based on the index.
Okay, so this is based on the task. And what is this task?
Task is what this thing, right?
1
Here
second.
I'm getting the
Task.
task from the preference. I'm getting the task list, right?
Uh-huh.
From the preference, I'm creating a
Okay, the task
task,
dictionary.
right? Yeah.
And this preference get task and claim preference. Okay, where you are getting this information, that degree way, that degree where you are maintaining?
Initially, I'm taking an integrity dictionary. I'm creating right on top.
But I think after you are updating the degree, now okay, in this part. Okay, okay. Okay, so you have sorted this based on this preference. Okay, Q. Okay, so this Q is only containing the vertex which have that in degree 0, correct? Okay, okay. And that you are only sorting that based on the preference. Okay, fine. So current vertex you are just removing from the Q and appending into the, okay, current vertex. Okay, this is the result. Fine. And after adding this, you are reducing the end degree of the each vertex which are actually neighbor of that vertex. Okay, so current vertex, what are the neighbor of these, and then you are reducing these -1, and again you are adding into the queue. Yeah, this is fine. Okay, so yeah, I'm just repeating again this logic. So what this code is working, how this code is working actually. So initially we are calling this. Okay, so you are using some built-in things. Okay, so in degree default integer.
Just to reduce the typing the code, sir.
Okay, actually I've never used this type of built-in sort things. So what this default dict is doing, int,
It will create whenever you give a key, it will create this thing with 0.
okay, it is creating the dictionary.
Yes.
Okay, degree, but we are not passing any number of keys or anything. So how?
It will create an empty dictionary whenever you initialize on this, right?
Okay, so by default that value will be passed as a 0.
Yes.
Okay, okay, okay. Okay, yeah, that is fine. So in degree is a dictionary which is getting the degree information, and after that we are updating the degree for each vertex in this. So, okay, so you can see for each node in the A list, this is adjacency list, and we are just reading the neighbors of each node, and based on that we are just increasing the in degree for that. Okay, so for neighbors we are increasing. So this neighbors means if we are coming from any node, so that means for neighbor, that means we will increment the in degree here. So we are coming, if we have any edge from any nodes, that we will increment the in degree by 1. So this part is actually creating a dictionary, and after that it is just creating the in degree information on the original graph. After that we are taking this my q, this is as a list, and in this for vertex in a list key in degree info. Okay, so we are checking that which vertex have in degree 0, and we are appending all these vertex into this queue. Okay, so that means this queue will always contain the information of in degree 0 vertex, and this is the another thing, sorted things. Okay, so this is creating the preference index. Okay, this is also, I'm not aware of this shortcut things. Okay, so this is okay, task.
Keep the key, I mean the element in the list and the index of the list. So it will create a, dictionary using task as the preference task as the key and the index as the value.
Okay, so preference task key and index as a value. Okay. Okay, so it is creating it. Yeah, this is dictionary comprehension. Okay. Okay, okay, fine. So this is creating a preference index dictionary. After that, this we are maintaining a result list, and we are checking this while my queue is not empty. Okay, so when we are writing this like while my queue, that means this is not empty. We'll repeat this process, and every time what we are doing, we are sorting this our that preference index dictionary, and then we are selecting this my queue. Okay, so we are updating this my queue. Okay, my
We
queue.
are updating the MyQ, sorting the MyQ used based on the preference indexes, And if
Okay,
the
so actually this Q term is actually giving some confusion, because Q you cannot modify it like this, sorted
yeah,
things. Okay, so because if you are using Q, that means you should we are supposing that you will use this
send
insert and delete operation only, insert from end and delete from first. Okay, but here you are also sorting this, so that is not possible operation for the Q. So instead of this Q, you can give any name like normal list. Okay.
okay, sir.
So this is not actually a queue if you're able to sort this. So, okay, so but if so, this is simply a collection of the node which have in degree 0, but we are also maintaining this preference things inside this, and we are sorting this all vertex based on that. And which, okay, so pop 0. So now the sort after sorting, the first preference node will actually come at the first place, and then we are removing from this list, and that will become current vertex. And after that, we are adding that vertex into our result. And because we are now removing one vertex from our graph, so that we have to reduce the in degree of each neighbors, because that means what are the outgoing edge from that current vertex, that is actually increasing in degree for the neighbors, so that we will, after removing this node, we should reduce the in degree for each neighbor. So that we are doing in this part. So for neighbor in a list of current vertex, in degree of neighbor will become minus equal to 1. So this will update for neighbors. If in degree of neighbors equal to 0, that means if after updating the in degree, if any vertex is now in degree become 0, then we will append that vertex into the queue, that list. Okay, and we will repeat the same process again and again. So this is actually a topological sort approach, and yeah, this is the correct logic for this problem. Okay, so you can so all can just try to write your code, which is actually you are able to understand, because this time actually I'm not able to actually understand this built-in function because I've never used. So do not try to learn the code. If you're not able to understand, just write your own code. Okay. So any query in this, any doubt in the third problem? Okay, any query, any doubt in problem third? Logic, code. Okay, no query. Okay, so then now quiz 1 is coming. So we will release the mock for that next week, and we will also conduct one revision session. And I think we will ask to TA also to just revise the things. But just so TA is already doing that revision things by the PYQ, previous year question. So you can just join that session also. Okay.
Sir, in the quiz one, whether the lot of code snippet will be there, meaning what
No,
is
not lot of person based on the code. The code will be given which you have already seen in your that content, like selection sort code is given, insertion sort code is given, some purpose, or maybe some linked list code is given for some specific task, but not too much question for the code based.
okay? Okay.
Okay, and also just try to solve this practice assignment questions of this. Okay, so because we have included that previous year question in the practice assignment this time, so that questions is also from the previous year questions.
Okay. So, and sir, this OPP one, it will happen on July 21st, right?
After quiz 2.
After quiz 2.
PDSA OPP is after quiz 2.
Okay, but
I
there
think
is,
you are referring to quiz that OPP 1. which is not our for
Oh,
PDSA.
so in PDSA there is only one OPP and that is 2, huh? Not 1.
There is only one OPP exam for PDSA, and that will happen with the OPP2 exam of the other course.
Okay. Then
Okay, not the
okay.
first time.
Okay,
That
okay.
will happen after week 10, actually, week 9 or 10.
So the sequence is quiz 1, quiz 2, and then the OPP.
OPP, yes.
Then the tournament.
Okay. And
Yes.
PDSA actually doesn't have any passing criteria, only the 20% weightage are there.
Yes.
Yeah, there is no separate passing criteria for OPP. Okay. Okay, then if you don't have any query, then we can close the session. You can practice this problem on portal also. Okay, so just after solving on here on the replit, also test on the portal.
Yeah, sure, sir.
Okay. Okay, then thanks
sir.
everyone. Yeah.
Thank you.
Okay.
Thank you, sir.
Thank you.
Yeah.